In today's class, we discuss about diffraction of light. So, diffraction of light is the bending of light waves around the edges of obstacle. So, diffraction is the phenomenon of bending of light around the edges of obstacle. What is diffraction? The phenomenon of bending of light waves. Bending of light waves around the edges of obstacle. Around the edges of obstacle. Okay. Example: color rings around the moon are observed due to the diffraction of light. Okay, the light is not easily observed in nature because the wavelength of light is very small. Wavelength of light is very small compared to the size of the obstacle. Wavelength of light is very small compared to the size of the obstacle. So, diffraction effect is announced when the size of the obstacle is comparable with the wavelength of the light. Okay. There are two types of diffraction of light. They are Fresnel diffraction and Fraunhofer diffraction. Fresnel diffraction and second one Fraunhofer diffraction. Fraunhofer diffraction. Okay. First we will discuss about the Fresnel diffraction. First one is Fresnel diffraction. So in this type of, generally diffraction effect is observed at the edges of obstacle. For example, this is the obstacle or this is slit. When light from this source incident on this obstacle, so this light is affect the diffraction. When light from the source is incident on the obstacle, it gets bends. The light gets bends due to the diffraction effects. So in Fresnel diffraction, the source and screen are placed at finite distance. In the Fresnel diffraction, the source and screen are placed at finite distance. That means for finite distance we get spherical wavefront and cylindrical wavefront. So for this type of diffraction, the wavefront is spherical. The wavefront is spherical or cylindrical. Okay. So Fresnel diffraction is obtained only when the obstacle is placed at an infinite distance from the source and the screen, or the wavefront is spherical or cylindrical. To get this spherical or cylindrical wavefront, get a point source like this. So light from this point source is incident on the obstacle like this. So when light coming from the point source is emit spherical wavefront. Light from this point source emits spherical wavefront. When this spherical wavefront incident on the obstacle, this undergoes diffraction. That means bending of light around the edges of the obstacle. Okay. When light gets diffracted, so this diffraction pattern is obtained on the screen, which is placed at a finite distance from the obstacle. So this is the obstacle. So for Fresnel diffraction, the source and screen are placed at only finite distance between the placed at finite distance. Okay. Next, second one is Fraunhofer diffraction. Fraunhofer diffraction. So this Fraunhofer diffraction is obtained when the source and screen are placed at infinite distance. The Fraunhofer diffraction is obtained when the source and screen are, both source and screen are placed at an infinite distance. Okay. In Fresnel diffraction, the source and the screen are placed at finite distance from the obstacle. But in Fraunhofer diffraction, the source and screen are placed at infinite distance from the obstacle. So, when the source is at infinity, we get plane wavefront. So, the wavefront is plane wavefront. So, in Fraunhofer diffraction, plane wavefront is used. Plane wavefront is used because for infinite distance we get plane wavefront. Okay, that means the source, both source and screen are placed at an infinite distance. Okay, for this we consider a point source which emits monochromatic light. Okay, this point source is made to pass through a convex lens because to get the parallel beam of light, because here for Fraunhofer diffraction we use the plane wavefront. For plane wavefront, screen is kept at an infinite distance. To avoid that, the convex lens is placed in front of the source, because when light from the source is incident on the convex lens, it gets refracted. After refraction, the parallel beam of light emerges out. So this parallel beam of light, the wavefront, for parallel beam of light, we get plane wavefront. That means by joining the locus of all this point, we get the plane wavefront. Okay, to get the plane wavefront, we use the convex lens. Okay. And the screen is placed at a infinite distance, but to avoid this, again we use one more convex lens. Let us call this as L1 and this as L2. Okay. After diffraction, this light rays, parallel beam of light is incident on the second lens, convex lens L2. Again after diffraction, they are focused on the screen at a point. That means they are converges at a point. Okay, so for this arrangement we use two convex lens to avoid kept the source and the screen at an infinite distance. Okay, so what is Fresnel diffraction? It is the source and in Fresnel diffraction, source and screen are placed at a finite distance, but in Fraunhofer diffraction, source and screen are placed at an infinite distance. So spherical or cylindrical wavefront is used, only plane wavefront is used. Okay. Diffraction at a single slit, that is called as Fraunhofer diffraction. We know that for Fraunhofer diffraction, the source and screen are placed at an infinite distance from the obstacle, or the wavefront is plane wavefront. So Fraunhofer consider two convex lens. First one is convex lens L1. This convex lens L1 is used to produce the parallel beam of light, because for parallel beam of light we get plane wavefront. Okay, so it took another convex lens like this. So this convex lens is called L2. So this convex lens is used to converge the diffracted light. Second convex lens is used to converge diffracted light. Okay, so he took a screen. The screen is placed at a distance. He took a screen to observe the diffraction pattern. Between the two convex lens, he take a slit. slit like this. Let us call this slit as A and B. AB is the slit. Okay. This slit is called AB. So this slit is placed between the two convex lens L1 and L2. So the distance, the screen is kept at a distance D from the slit. Okay. So D is the distance between the screen and slit. So this slit width is called as D. D is the width of the slit. Sorry, let us call this as A. A is the slit width. Okay. So we took a source of light. This is the arrangement of Fraunhofer diffraction. For Fraunhofer diffraction, we take two convex lens L1 and L2. In between two convex lens, we placed a slit, and to observe the diffraction pattern, he took a screen. Okay. When light from the source, when source emits light, or when source emits monochromatic light. Monochromatic light means single colored light. Monochromatic light. When source emits monochromatic light, so this light is made to fall on the convex lens L1. This light is made to fall on the convex lens like this L1. Okay. When light falls on the convex lens L1, it undergoes refraction. So after refraction, the parallel beam of light are obtained. After refraction, the parallel beam of lights are obtained. So this parallel beam of light is because to get the plane wavefront. That means the convex lens emerges parallel beam of light like this. So by joining the locus of all these points, we will get a plane wavefront. That means here plane wavefront is incident on the slit. Okay. So when plane wavefront is incident on the slit, what is that slit? That slit is AB. Plane wavefront is incident on the slit, that is slit AB. Okay. It when light incident on the plane wavefront incident on the slit, that means it undergoes diffraction, because the slit AB itself acts as an obstacle. Okay, when light passes through an obstacle, edges of obstacle, it undergoes diffraction. Okay, so when the plane wavefront incident on the slit AB, it undergoes diffraction. And after diffraction, the diffracted rays are passed through the lens L2. And after the diffraction, this diffracted rays are passed through the lens L2. Again, this diffracted ray reaches the lens L2, it undergoes refraction. After refraction, this diffracted rays are converges at a point on the screen like this. After refraction, they converges at a point on the screen like this. After refraction, they converges at a point on the screen like this. Let us call this point as O. Passing through the convex lens, they converges at a point on the screen. Let us call that point as O. Okay. So here the point O is at equidistance from the point A and B. O is at equidistance from the point A and B. When plane wavefront is incident on the slit, each point on the slit act as a source of secondary disturbance. According to Heidel's principle, each point on the wavefront is a source of secondary disturbance called secondary wavelets. That means when plane wavefront is incident on the slits, the small waves are emitted. That means that are called as secondary wavelets. These secondary wavelets are superposed on each other and produces a diffraction pattern like this. Okay, so here the point A and B are the same distance from the point O. When these wavelets are overlapped with each other, because of the same distance, it undergoes constructive interference. Therefore, we get bright fringe at the center. at the central. That is called as central bright fringe. The interference pattern as a diffraction pattern like this. That means we'll get central bright fringe. Okay. Next, secondary wavelengths from the after. The secondary wavelengths from A and B also diffracted through an angle theta. They are also diffracted through an angle theta like this. Again, you will get diffracted wave at the point P, at some point say P. Like this. Diffraction at a point P. So, and after diffraction, they reach at a point on the screen, and we have to call that point as P. Okay. So, based on intensity, the point P will be maxima or minima. Maxima is the maximum intensity point, or minima is the minimum intensity point. Okay. From the figure, path difference is equal to. From the figure, path difference is equal to. What is that path difference? Let us call this perpendicular line as n. So path difference is equal to Bn. So to derive this Bn, to write the expression for this Bn, we define sin theta. Sin theta, what is sin theta from the triangle ABN? So from the triangle ABN, sin theta is opposite by hypotenuse. The opposite side is Bn and hypotenuse side is AB. So sin theta is equal to Bn by AB is A, is the width of this slit. So Bn is equal to A sin theta. So from the figure, path difference is equal to Bn, that will be equal to A sin theta, where theta is the angle of diffraction. Theta is the angle of diffraction. Okay. Next, we have write condition for diffraction minima. For diffraction minima, path difference is equal to lambda. Path difference is equal to lambda. Now, divide the slit into two halves. Slit into two halves. That is, path difference is lambda by 2. So, each half forms a wavefront. So these each half forms a wavelets, secondary wavelets, and these secondary wavelets reach at a point P out of phase. If they reach the point P out of phase, we get the destructive interference. That means at the point P, the intensity is minimum. So for that we get first minima. So for first minima, that means first minimum intensity point. For first minima, path difference is equal to what is that path difference? A sin theta. For first minima, we can write that as A sin theta 1. So path difference is lambda. So lambda is equal to A sin theta 1. Here the wavelets are diffracted through very small angle, that is for small angle sin theta is approximately theta. So sin theta 1 is approximately equal to theta 1. Therefore lambda is equal to A theta 1. Theta 1 is equal to lambda by A. This is the condition for first minima. Okay. In general, we write this as for nth minima. For nth minimum, we write theta n is equal to n lambda by a. For first minimum, right, theta is equal to lambda by a. For nth minimum, theta n is equal to n lambda by a, where n is equal to 1, 2, 3. For first minimum, we put n is equal to 1, we get lambda by a. So for second minimum, we put n is equal to 2, so theta 2 is equal to 2 lambda by a. For third minimum, we will put n is equal to 3, so theta 3 is equal to 3 lambda by a, like that. Okay. Next, we should write condition for diffraction maximum. Condition for diffraction maximum. Next, for for diffraction maximum, path difference is equal to a sin theta. Okay, path difference is equal to a sin theta. For this maximum, the intensity at the point is maximum. Okay, so for maximum, path difference is an integral multiple of wavelength. That is, a sin theta is equal to the integral multiple of wavelength, that is lambda by 2. Then constructive interference takes place at the point P. Therefore, for nth maximum, theta n is equal to, for nth maximum, path difference is equal to a sin theta n. For nth maximum, path difference is equal to a sin theta n. That will be equal to integral multiple of lambda by 2, that is n plus of into lambda. Okay, here n is an integer, lambda is the wavelength of the light. So which implies a sin theta n is equal to n plus of lambda. So theta is very small, then sin theta n is approximately equal to theta n. You get a theta n is equal to n plus half into lambda, or theta n is equal to n plus half into lambda by 8. This is the condition for nth maxima. At maximum point, intensity is maximum. Okay. At minimum point, intensity is minimum. So, what is the condition for diffraction minima? Theta n is equal to n lambda by a. Now, what is the condition for diffraction maxima? Theta n is equal to n plus half into lambda by a.